Hi guys, I've just made this video so I can teach you about algorithms and pseudocode for the up and coming exam. Now, personally, I think this is stupid to add this into methods and specialist. Um, I understand that it's got something to do with the course in regards to we use algorithms and well, we don't use pseudocode all the time, but we use algorithms all the time. We just don't specifically say that they're algorithms. So learning how to factorize something, we use some sort of algorithm. We don't all use the same algorithm because we don't factorize the same way. Well, not always. Someone could factorize a quadratic using a cross swords method. Someone could just do it by inspection. So there are algorithms out there to factorize, but we don't use a specific one for every single person. We can use different ones. And basically all an algorithm is instructions, like making a cake. And there'll be some sort of repetition usually within the algorithm that will calculate something over and over until you get an answer. So this year you would have learnt Newton's method, and all Newton's method does, it's an algorithm in itself. We get a starting point. From that starting point we create a tangent. We get the x-intercept to approximate the value of this actual x-intercept here. We then create another tangent, and then we get the x-intercept here. And then from that point, we then go to the graph, and then we create another tangent. And eventually we'll see that this value here is going to become very close to the real value of the x-intercept there. So all we're doing is getting the x-intercept of the tangent for a particular point, and then doing the same thing again at that point, find the tangent, get the x-intercept, and we repeat the process. So that's an algorithm in itself. So here, the definition in the textbook, it's a finite, unambiguous sequence. So it's got to stop. That's what finite is. Can't go on to infinity. And it's an instruction for performing a specific task. So you've already seen many algorithms in your lifetime or study of maths, completing the square for any quadratic polynomial, or for baking a cake. I don't know, and where I got that from. All pseudocode is like a mixture of real computer programming code and then a mixture of English. So it's describing an algorithm that's somewhere in between our normal speaking language and a more formal programming language. Now, I studied computer science at university, so I've done all this stuff a lot before, and I don't know how they expect to get this content into you as well as the normal methods course. And I don't know how far they want you to go. I think it's a bit stupid. But, so pseudocode, all it is, computers don't understand English. Well, they're starting to now with AI. But they don't understand English, so what you've got to do, they have these interpreters basically. So if you speak in English, there's an in-between, an interpreter, that has to convert it to a language that the computer can understand. And we call that coding or programming. So it depends on, there's lots of different programming languages, Java, PHP, JavaScript. There's so many, it's not funny. Visual Basic, C++, C. Basically, they all interpret things in different ways. So if you write something in C++, the interpreter understands it in C++. With pseudocode, basically what we're aiming to do is write an algorithm that, not that a computer understands, that someone can read through and follow the step by step with a bit of English and a bit of mathematics and variables and all that sort of stuff, a bit of coding in it. So here, a computer can be defined as a machine that carries out the instructions of algorithms. Computers consist of both hardware, so that's like the physical things, and then software, they are the ones that carry out the instructions, like Microsoft Word. So if you push the letter A, the keyboard interprets that, sends it to Microsoft Word. Microsoft Word goes, hey, how do you want me to format that? And then it puts it on the screen for you to look at. So that's an algorithm in itself. The process of taking an algorithm and writing it in a programming language is called coding. We don't actually have to code. We have to write pseudocode possibly. I don't think they're going to get you to write pseudocode. More so just read it and interpret it. So we'll be looking at algorithms in pseudocode, and it's informal notation that's very similar to natural language with a lot of less than's and greater thans and variable storing. In order to actually implement the algorithm on your computer, they must be translated to a specific programming language. So there's a list of, but there's heaps more. In this section, we start to become more slightly formal in the language we use to talk about algorithms and in the notation we use to describe them. So we've used variables before in maths. In coding, they don't just have one type of variable. I mean, we've got multiple types of variables in maths as well, because we could use a matrix or a list, and they're usually called, in coding, they're called arrays. So an array can store multiple pieces of information, and you can have a multiple dimensional array, but we don't need to worry about that. If we want to assign a variable, we say, there's my variable x. We want to assign the value 3 into the variable x. Now, usually in programming, we would have to do what's called declaring a variable. So that the computer can understand, we'd actually declare the variable itself and call it like an int, which stands for integer x. So that tells the computer that we're going to store an integer in there, or you could store a float x. A float is a number, I think it's, depends on the language, but it's 32 bits. So 32 bits of information can be stored in a float. You can have doubles, which are twice as large. There's lots of different stuff. But all we do here is we just assign values to a variable. So here is step one. If I assign 3 to x, and then I assign x to y, here x would equal 3. Here y would equal 3. And then here, this would overwrite the previous value of x. So now x would equal 4. So after following these steps, we have x is 4 and y is 3. Now, often new values are assigned to a variable based on the old value. So my new value is my old value plus 5. So it's saying replace a with the current value of a plus 5. Here, replace a with 2 times the current value of a. So here, initially a is 3. Now it's 8 because I've added 5 to it. Here, a is 3. If I replace it with 2a, a now becomes 6. Now, when we work through code, we might want to complete something over and over again. So here we might want to continually add 5 to a. So when we have an algorithm, the order of the steps is very important. They're usually carried out one after one, and we call them iterations. So if I told you to do this once, that's my first iteration. If I asked you to do it again, that's my second iteration. So if I asked you to perform 5 iterations, you would have to do that 5 times. So iteration is just another word, I guess, for steps. Selection, it's when we choose to do a specific thing based on some some comparison, I guess you would say. Looping constructs allow us to repeat in a controlled way. So an iteration is completing something over and over again. Here, we can have a look at an example of an iteration for an arithmetic sequence. So, write an algorithm to find the first 6 terms of an arithmetic sequence. So for anyone who doesn't know what arithmetic means, it means to add them together. With the first term 10, so starting at 10, and the common difference is 7. So we'd go 10, 17, 24, 31, 38, 45. That's the sequence we should get. Now, what we want to start with here, it says the first term is 10. So we're going to say T is where we store our term, and N is the number of the term. Now, we want to find the first 6 terms. So, first off, we print N and we print T. So we know N is 1, our first term is 1, and our first actual term is 10. We then say our term is our previous term plus 7. So 10 plus 7 is 17, and N is N plus 1, so N is now 2. We print them out. So first we printed those two, now we're printing these two. Repeat from step 3 while N is less than 6. So not when it's equal to 6. So here, we know N is now 2. If we go up to here, we get T is my previous value of T, which is 17 plus 7. N is my previous value of N plus 2, which is 3. Print them both. Repeat from step 3 while N is less than 6. So 3 is less than 6, we go up to here. We add 7 onto our previous value, we get 31. We add 1 onto our previous value of N because it's the next term. We print N and T. That's them. We check and say, okay, N now is 4. Is that less than 6? Yes, it is. So we go back up to here again. We then add 3 on, so we get, 7 on, we get 38. We then add 1 onto N. We get 5. We print those two values and then we say, okay, is 5 less than 6? Yes, it is. So we've got to repeat it again. When we get up to here, we get T is T plus 7, so 45. N is N plus 1, so 6. We print them, and when we come down to here, N is no longer less than 6. So we said repeat from step 3 while N is less than 6, but it's not anymore. So then we end. So this is our sequence, which is exactly what we said it was going to be when we did it by hand at first. And this is our term number. So term number 1, term number 2, term number 3, term number 4, term number 5, term number 6. Okay, so this is our algorithm. Assign 10 to T and assign 1 to N. Print those values. Assign T to be T plus 7 and N to be N plus 1. Print them out. Check and see if N is less than 6. If it is, then we go back and repeat that step. If it's not, then we end. So that's our algorithm. Now, sometimes we need to decide, like if we've got a hybrid function, which function we need to use. Maybe if N is greater than 0 or N is less than 0. So decision making allows us to specify whether certain steps will be followed based on some condition or a selection. We can use an instruction if then. So if something occurs, then do this. We illustrate selection in the next example by considering a piecewise defined sequence. So here, our terms using natural numbers Anyone doesn't remember what natural numbers is? 1, 2, 3 to infinity, but obviously it can't include infinity because it's not a real number. Write an algorithm to generate the first n terms of this sequence. So we want the first n terms, so we want to go Tn, that's our first term, and n must start off being 1 because we want the first n terms. So the first thing we want to do is assign 1 to n if we're going to write an algorithm to generate the first n terms. If n is even, then our term is this. Otherwise, our term is this because it must be odd. If it's not even, it's got to be odd. We then print our value of t. We add 1 to n. Now, you don't have to know this, but that means increment. Increment means to add 1 to a value. So we increment n by 1. Repeat from step 2 while n is less than capital N. So n is some value. We'll tell it when to stop by giving it that value at the start. Okay, so here it says demonstrate the algorithm for n is 6 with a table of values. So initially we know n is 1. If we sub 1 into here, we've got to use the otherwise, so we get 4. We print 4. We then increment n, it becomes 2. Well, n is less than or equal to n. Is 2 less than or equal to 6? Yes, it is. So we go back to here. If n is even, it is. 2 times 2 plus 4 is 8. We then print that value and then increment n, and we get 3. Is 3 less than or equal to 6? It is. So we go back up here. N isn't even, it's odd. So t is n plus 3, and we know n is 3, so we get 6. We then say print 6. We then store 3 into here, and we get n is 3 plus 1, which is 4. Now, n is 4. If n is even, do this. So 2 times 4 is 12. 8 plus 4 is 12. Print t. We did 12. Increment n by 1, so we get 5. Is 5 less than or equal to 6? Yes, it is. Go back up to here. If n is even, it's not. It's odd. So from here, we get 5 plus 3, which is 8. We then print it. We then increment it by 1, so we get 6. And then we go back up to here. If n is even, which it is, sub it into there. 2 6s are 12, plus 4 is 16. Print t, 16. Add 1 to n, we get 7. Is 7 less than or equal to 6? It's not. So we stop. So you would need to, in this question, you would need to, well, you know it's going to start with 1, but you'd need to know what the upper value of n is, like what you can't do it forever because you'd never actually get a solution. That's why we say it's a finite. It's a finite. It's a finite, unambiguous. So there's a definite answer to it. It's not ambiguous. It's not like English, or if your teacher doesn't like you, they can mark you down. Okay, for each of the following algorithms, give a table of values showing the values of a after each iteration. So a is 10, n is 1. A is a plus 5, 15. N is n plus 1, 2. Repeat while n is less than or equal to 5, or 2 is less than or equal to 5. So we go back up to the stop. up to step 2, we add 5, add 1. Is 3 less than 5? Yes. Add 5, add 1. Is 4 less than 5? Yes. Add 5, add 1. Is 5 less than 5? Less than or equal to 5? Yes. Add 5, we get 35. Add 1, we get 6. Is 6 less than or equal to 5? No. So we stop there. Now, if it asked you what the output is, well, you'd have to print. In here, you would have to say print A to get some sort of output. That's just what the value of n is when, that's the value of A when n is equal to 6. This second one, A is 2, n is 1. A is 3 times A, so that's 6. Add 1 to n. Repeat while n is less than or equal to 4. Well, it is. A is 3A, so it's 18. N is n plus 1. N is less than or equal to 4, yes. A is 3A, 54. N is 3 plus 1, which is 4. Is n less than or equal to 4? Yeah, it's equal to 4. We've got to multiply it by 3. We get 162. N is 5. Is 5 less than or equal to 4? No. So we stop. So basically, in exams, all you're really going to be doing is filling out these tables, like working through the steps. Now, it does get a little bit more complex because it does get a little bit more complex because the actual questions themselves, they include more than just one statement usually. They might have multiple statements. Sorry, I just got a text on my phone, so I was checking that. Okay, so we can use if-then blocks. So if something occurs, then do something. So here, this is a while, which is kind of like an if-then. So if something is less than something, do this. That's an if-then statement. But we can also have an if-then and then an else. So if something occurs, do that. Otherwise, do this. So if something is even, do this. Otherwise, it's odd. So otherwise, it must be odd. So that's when we use an if, then, and an else. We can also use an if, then, and an else if. So if something occurs, then do this. Else if something else occurs, then do this. And then if all else fails, do the last statement. So these are useful for selecting what to do based on particular values. Now, it doesn't always have to be numbers. It can be something called strings as well, but we obviously are not going to deal with that in maths. So, yeah. Okay, so here, using pseudocode, write an algorithm to find the maximum of two numbers A and B. So like I said, it's highly unlikely that you're going to have to write the code. Firstly, I'm going to define two inputs. So this is, input means it's got to come from a user. So someone has to put these in. So input A and B, there are two numbers. We can say if A is greater than or equal to B, then print out the value of A. Otherwise, print out the value of B. And that's it. So the end if just tells us to stop that if statement. So if A is greater than or equal to B, then we print the A value. Otherwise, B must be greater than A. That's all it is. Write an algorithm that assigns a letter grade based on a mark out of 100. So, firstly here, we would have to have them input their mark. Now, it depends on what grade you want to give. So let's say 90 plus is an A. 80 plus is a B. 70 plus is a C. 55 plus is a D. And then, let's go 50 plus. 50 plus is a D. And then 0 plus is an E. So if we get 90 or above, we get an A. So if our mark is greater than or equal to 90, then we print A. Else, if the mark is greater than or equal to 80, print B. Now, you don't have to worry about the fact that you might print A and print B, because we would only print A if we got higher than 80. Here, if mark is greater than 80, the assumption that it's got to be less than 90, because it would have gone into there, and once it goes into this, it jumps out to the end if. So we've got 80 or greater, print B, but it's really, and it's less than 90. Else, if mark is greater than or equal to 70, then print C. Else, if mark is greater than or equal to 50, then print D. Now the last one is just going to be an else statement, because if they didn't get any of these, we don't have to say else if, we just say else print you failed, you loser. No, only kidding. Well, sort of not. Print E. End if. Now, what this does, it goes, okay, just say our mark is 76. If mark is greater than or equal to 90, well, it's not, so we go to the next statement. Else if mark is greater than or equal to 80, it's not, so we go to the next statement. Else if mark is greater than or equal to 70, it is. Print C, and then it jumps to the end if, and then it breaks out. So as soon as you go into one of those if statements, it prints that, and then it automatically jumps to the end. Like it can't print out two statements. Okay, so that's selections. The next one is for loops. And this is when you repeat something for a number of times or until you reach a certain error. But yeah, I think this one's usually a number of times. So a for loop allows us to repeat the process a number of times. A while loop is usually until we get a certain condition to occur. So this is performing one iteration for each term in the specified finite sequence. So finite just means ending sequence. We use loops. We use for loops based on the following template. So from I, so that's our variable I. That's the number that we move through. We're starting with I is 1, and then we're going up to some value n. Follow these instructions. So this for loop uses a sequence 1, 2, 3, 4, all the way up to n. We repeat the condition n times with the variable I taking the values 1, 2, 3, 4, all the way up to n. In the following example, we see a desk check. Now, this is something the book's made up. I've never heard of a desk check before. And I did computing a while ago, but never heard of a desk check. We would have testing tables. That's probably sort of, I guess, what it is. Okay, carry out a desk check of the algorithm by performing the algorithm step by step and constructing a table of values for all variables after each step. So this is what you're going to do in an exam. They're going to give you an algorithm and then you've got to work out what the output is. So sum, we're assigning 0 to it. So I'm going to say that's my initial value. When we talk about iterations, pass 1 is iteration 1. So for I equals 1 to 4, we go sum is sum plus I squared. So here, if I is 1 and sum is 0, 0 plus 1 squared is 1. So sum is now 1. Now, when we get to here, we go back up here. We don't have to say I is equal to I plus 1. When you get to the end of this N4 statement, you've got to go back up to the top. And we know now I would be equal to 2. So sum is 1, my current value of sum, plus I squared. Now I is now 2. 2 squared. So now we get 5. We go back up to the top, we add 1 to I, it becomes 3. And we say for 1 to 3, so now 3, sum is equal to 5 plus 3 squared. So 5 plus 9 is 14. And then we then go again, add 1 to I, we now get I is 4. For I equals 1 to 4, so now we're at the limit of 4. Sum is equal to sum, which is 14, plus 4 squared, 16. We get 30. Now, if I add 1 to I would get 5, so we don't do that anymore. It then says to print sum. So our output is 30. That's the sum of this sequence. It's 30 after that many iterations, 4 iterations. Okay. Now, so this is the desk check, and this allows you to see what the inputs are at each iteration. That's the value of I, and then that's the value of sum. Okay, using pseudocode, write an algorithm for the sum of the first n terms of this sequence. So here, we just want to write an algorithm that outputs these numbers. Same thing. We would start with sum being 0. We want to add these values together. So the first n terms of the algorithm. So input n. So you would have to say how many times you would, how many iterations you would want to go through here. We know for starters, we want to go for I from 1 to n, because we want to start at our first term and go up to our nth term. Now, we want our sum to be our previous sum plus 1 on I cubed. Because that's first time round, I is 1, I is 2, I is 3. And then we want it to repeat up to n. And then print out the sum. So initially, we know that our sum is 0. We'd ask for the input of n, and when it says to perform a desk check of 5, that would be equal to 5. So now we're effectively saying for I from 1 to 5, let's do that in a different color. From 1 to 5, sum is equal to sum plus 1 on I squared. So in our first step through, I is 1. If I sub 1 into here, we get sum is sum, which is 0, plus 1 on 1's cubed. Now, a few of you might get confused if you do specialist because you might think that's negative I. 0 plus 1 is 1. So our first pass, we get 1. We then end our 4 and go back up to the top. Now we know I is 2. Sum is 1 plus 1 on 8, because if I put 2 into that, I get 1 on 8. So I get 9 on 8, and that's 2. We then go back and do it again. This time, I is 3. So sum is 9 on 8 plus 1 on 3 cubed, 27. Now I'm just going to do it exact for the moment. 9 on 8 plus 1 on 27, 251 on 216. Now, our next one, n is now equal to, I is now equal to 4. So we get 251 on 216 plus 1 on 64. So plus 1 on 64. 2035 on 1728. And then our last one, we've got 5. It's just that plus 1 on our previous value plus 1 on 125. 256103 over 216000. Now, let's convert them all to decimals. So, 0 plus 1 on 1 cubed. Our answer plus 1 on 2 cubed. Our answer plus 1 on 3 cubed. Our answer plus 1 on 4 cubed. Our answer plus 1 on 5 cubed. And decimals. So the last one was 1.185662, I think. 1.177662. Uh, 1.62037. That's 1 and 125, I think. 1 and 1/8. Yep. Okay. So there's our first up until n equals 5 to 6 decimal places. So we knew that our sum, we always start our sum off being 0 because we're not adding anything onto it. And n is what we need the user, that's why we call it an input, user input. The value of n tells us how many times to keep repeating this thing. So that's a for loop where we have a certain number of iterations, certain number of repetitions that we want to perform. The next one is a while loop. So when we have a while loop, we might want to check something out specific. So like whether the error that we have, just say we've got an x-intercept, that's our actual intercept, and then this value here, that could be like 1.2, and this value here could be 1.3, but we could get a guess of 1.4. So we'd say, well, our error is still too large. We want to keep repeating this thing over until the difference between our actual value and our estimated value is 0.1. So that's when you would use a while loop, when you want to keep going until you want to achieve a certain accuracy in your answer. So it's another means of repeatedly executing the same set of instructions. It's useful when you don't know how many times you want to repeat it. You just want to keep going until you get a certain accuracy. It performs them indefinitely as long as some condition remains true. Now, anyone who's done coding before will know if you start a while loop and it never ends, it's going to crash your computer because all it's going to do is chew up your memory trying to find an answer that doesn't actually exist. So that's why you've got to be careful when you're programming, because you can create what's called an infinite loop where it just keeps going round and round in circles. So here we want to write an algorithm that divides 72 by 14 and returns the quotient and the remainder. So we want to know how many times 14 goes into 72 and then work out what the remainder is. So let's set our count, which is going to be how many times it divides. Let's set that to be 0. And our remainder, when we start off, is 72. Firstly, if the remainder is greater than or equal to 14, because we're dividing it by 14, as long as the remainder is greater than 14, it's still going to fit into 14. So if the remainder is greater than 14, we add 1 to our count. So we say count is our previous count value plus 1. We then subtract 14 from 72. So we can say our remainder, need more room, our remainder is equal to, is our old remainder minus 14. So when you code, you learn to create indents so that your code is easier to read. So here, count is our previous count value plus 1. Remainder is our previous remainder value minus 14. And then end while. Now it's only going to break from that end while, well, it's going to break from the while statement if remainder becomes less than 14. All right, so let's have a look. Initially, our count 0, our remainder 72. The first time we go into this loop, our remainder 72 is greater than 14. So count, we add 1 to it. Remainder is remainder, take away 14. So if I take away 14 from that, I get 58. We then go back up to the start. Is remainder greater than or equal to 14? Yes, it is. Add 1 to count, we get 2. Take 14 away from remainder, we end up with 44. Go back up to the top again. Is remainder greater than 14? Yes, it is. Add 1 to my count, so we get 3. Take away 14 from that, we get 30. Go back up to the start again. Is remainder greater than or equal to 14? Yes, it is. Add 1 to count. Take away 14 from 30, we get 16. Go back up to the top. Is remainder greater than 14? Yes, it is. It's 16. Add 1 to our count. Count is now 5. Remainder take away 16 is 2. Is remainder greater than 14? No, it's 2. So we stop. So 72 divided by 14 is print, count, and remainder. So it's 5, remainder 2. Now, if this was real coding, you would usually say print, count, plus, remainder, and then the actual variable remainder. But here, we're just outputting the count and the remainder, which would be those two values. Okay. The algorithm shown below provides an approximation to root 11. Perform a desk check for this algorithm. Give values correct to 6 decimal places. So we're going to use a calculator for this. 11 plus 10 to the negative 4. 11 plus 10 to the negative 4 is 11.0001. And then 11 minus 10 to the 4 is 10.9999. Now, firstly, we assign a to be 3, and we know a squared will be 9. So if a squared is greater than that, or a squared is less than that, we perform this operation. So here, when we square 3, we get 9. Now, pass 1, is 9 greater than that? No, it's not. Is it less than that? Yes, it is. So we get a is 0.5 times 9 plus 11 on 9. So 0.5 times, let's say x plus 11 on x. And we know x equals 9. So that's our first value. A is a half of a plus 11 on a, 9 plus 11 on a. All right, so in this case here, what did we get? 0.5, that should be 3, sorry, not 9. So we get 3.33333. So here, 3.333, etc. And then we can say that squared is 11.1111. Now, is 11.1111? That was 11.0001, and that was 10.9999. Is that outside of that boundary? Yes, it is. So now, A, we use this previous value of A, 3.33333. So we say this, given that, is that value. We get 3.316667. 3.316667. Let's just round it. And then if we square that, we get 11.000278. Now that's still greater than that. So we then say this, not that value. We then use that value. We get 3.31662. 3.31662. 48. If I then square that, we get 11. So we know that that is effectively the square root of that. Because when we square that, we get 11. So if we square root 11, we get that. So correct at 6 decimal places, the square root of 11 is 3.31662.5. Let's square root it and see what we get. Square root 11. You can see they're the same. Okay. So, here we've got a few to work through. The easiest thing to do is to create a table. So, A and B. Don't know why I didn't put a table here, to be honest. A, B. So input A, B. A is 2, B is 3. If A squared, let's put that here. Don't know why I didn't do that as well. So that is A squared minus B. So that's 1. Is that less than 20? Yes, it is. B is now B plus 2A. So it's 3 plus 4, which is 7. A is now A plus 2. So my value is now 4. 4 squared minus 7. 16 minus 7 is less than 20. Yeah, it is. It's 9. B is now B plus 2A. So 2 times that is 8 plus 7 is 15. A is now A plus 2, so that's 6. Is 36 take away 15? It's 21. Is that greater than 20? Is it less than or equal to 20? No. So print A. A is 6. B is 15. Hopefully that makes sense. Okay. Now, the next one, we'll do the same sort of table, and this is pretty much what you've got to do. We know A is 3, B is 2. Stupid thing. So initially, I don't know how many times this is going to take, so, oops, didn't mean to put the arrow, but I don't care. Okay, A squared minus B. A is 3, B is 2, 9 minus 4 is 5. So because it's less than 20, B is B plus 2 times A. So 2 plus 6 is 8. A is A plus 2, 5. 25 minus 8 is 17. Is that less than 20? Yes. We know B is B, current B value, plus 2A, we get 18. We know that A is A plus 2, we get 7. 49, take away 18. We know that is 31. So 31 is not less than 20. So we stop here, and we know A is 7 and B is 18. Okay, so we didn't need all of those steps. We just had to stop when A squared minus B was less than 20. Okay, consider this block of code on the right. We've got to step through these, performing a desk check. Okay, so initially it tells us A is 64, B is 120. Input A, B, we've done that. Well, A doesn't equal B, they're not the same. If A is less than B, it is. C is equal to whatever A was, 64. A is B minus A. 120 minus 64 is 56. A is B minus A, so that's 56. And C is B, so that's 64. Okay, we skip the else, and let me go back up. If A is less than B, it is. C is equal to A, 56. A is equal to B minus C, that's going to be 8, and that's 56. Is A less than B? Yes, it is. C is whatever A is, so that's 8. A is that minus that, which is 46. And C goes into B, so that's 8. Is A less than B? No, it's not. C becomes B. B becomes A minus that, so 46 minus 8 is 38. C goes into A. Okay, is A less than B? Yes, it is. C is A. A is B minus C, so that's 30. And then that's C. I think my pen's gone flat. Okay. I'm going to take 2 minutes to have a toilet break. I'll be back in a second. I don't know if I can pause this thing. I'll be back. Okay, so A was 30 and B was C, so 8. Okay, if A is less than B, it's not. C becomes B becomes B. B becomes A minus B, so what's that? 22. A becomes C, 8. Is that less than that? Yes, it is. C becomes A. A becomes B minus A, 14. B becomes C, 8. Is that less than that? No, it's not. So B goes into C. B is A minus B, so it's 6. And then A becomes C. I have a feeling I may have stuffed this one up because I feel like when I put this together, I checked this and I ended up with 8. Does 8 go into 120? It does. Should be 8. So what have I done? I've just done a simple arithmetic error somewhere. Let me go back again. Stupid. Okay. 64, 120. A doesn't equal B. A is less than B. Yes, it is. C is A, 64. A is B minus A. 120 minus 64 is 56. B is C, 64. Is that less than that? Yes, it is. C is A, 56. A is B minus A, 8. B is C, 56. Is A less than B? Yes, it is. C is A. A is B minus A, 48. B is C. C is B, sorry. Yeah, B is C. Okay, is that less than that? No, it's not, so we go down to here. C is B. B is A minus B, which is 40. A is C. This seems better. Is that less than that? Yes, it is, so we go up here. C is A, 8. A is B minus A, 32. C is B, 8. That's not less than that, so we go down here. B goes into C, 8. That's that minus that, which is 24. A is C, 8. Is that less than that? Yes, it is. A is C. A is B minus A, 16. That's 8. And then lastly, that's not less than that, so we go to else. B is C. Sorry, C is B. A minus B, 16 minus 8 is 8. A becomes C, 8. Now, when we go up to our while A doesn't equal B, A is equal to 8, B is equal to 8. So then we go down and then we print A. So A is equal to 8. Now, what this algorithm does is it finds the highest common factor. The largest thing that fits into both of these numbers is 8. So let's have a look. If we do the same thing here, 360, 100. A is greater than B, so B goes into C. B is A minus B, so 260. A is C, 100. That's less than that, so we now go here. A goes into C. A is B minus C, which is 160. And C goes into B, 100. Is A less than B? No, it's not, so we go down here. B goes into C. B is A minus B, so that's 60. A is 100. Is that less than that? No, it's not, so we come down here. B goes into C, 60. B is A minus B, which is 40. C is A. Sorry, A is C, so 60. Is that less than that? No, so we come down to the bottom one again. C is B, 40. B is A minus that, which is 20. A is C, which is 40. Now, is that less than that? No, it's not. So we come down to the bottom one again. B goes into C, 20. B is A minus B, which is 20. And A is C, which is 20. So they're all the same now. So A is equal to 20. And that's our highest common factor of 360 and 100. Then our last one, can't move that thing out of the way, 144, 896. Is 144 less than 896? It is. C is now A, 144. A is 896 minus 144, 257. And then that becomes 144. Now, is that less than that? No, it's not, so we come down here. B goes into C, 144. B is that minus that. 752 minus 144 is 608. And then that becomes 144. A becomes C. 144 is less than 608, so we go up here. C becomes A. A becomes B minus C. 608 minus 144, 464. That's A, I think. And C goes into B, so 144. Is A less than B? No, so we come down here. Put B into C, 144. B is A minus 464 minus 144 is 320, and that's going to be 144. Is A less than that? Yeah, we know it is. That stays as 144. A is 320 minus 144. We know 6, 7, 176. That was A, I think, because it was less than. A becomes that. Yep. And then that becomes 144. Is A less than B? No, it's not. So B goes into C, 144. B is that minus that, so it's going to be 32. And then that's 144. We know 144 is greater than 132. So C becomes B. B is that minus it. So 144 minus 132 is 112. And then that, A will become C, 32. 32 is less than 112, so we go up to the top one. A goes into C. A is B minus A, so what's that going to be? 80. And then C goes into there, 32. Is A less than B? No, it's not, so we come down to here. B goes into C. B is A minus B, so 48. And then that is 32. Is 32 less than 48? Yes, it is. So we go up here. A goes into C. Say 32. A is B minus A, 16. C is B, say 32. Is that less than that? Yes, it is. So we go to the top. A goes into C, 16. A is B minus A, 16. C is B, 16. Therefore, A is 16. So, the highest common factor of those two numbers is 16. And I forgot to write the second part of the question. It said, what does this actually give you? This algorithm gives you the highest common factor of two numbers, or two integers, I should say. Okay, now the last couple of things, I honestly didn't think you're going to have to know how to use these, but I know it's easy for me to say. It's not that hard because I've been doing this for like 15 years, since I was a 12-year-old. I'm not really that young. Yeah. So everything we've done so far is kind of like a function in itself. If you think about it, if I said to you, I wanted you to find the highest common factor, or what else do we do? Is it LCD, lowest common divisor, all that sort of stuff? What we could do is we could write a function. Actually, let's say highest common factor. We could have a function called highest common factor, which is that one. And then we can have a function, and we could call it max. Now, in both cases, I could pass these two numbers, A and B, and this one here, I could pass that, A and B. So in this case here, these values of A and B, what we would do is we would have a function which calculates stuff, and all we do is pass it two values. We call them parameters, A and B, and then it would output, this function would output that value. And what we actually do is we say return. So if I call the function HCF, so that means the function HCF, if we want to call it, we just say HCF, and then I could pass it the number. I want the highest common factor of 10 and 20. And that calls that function. It uses the value A is 10, B is 20, and then it returns the value 10. So this thing here, if I said what's HCF of 10 and 20, I would get a value of 10, the highest common factor. So a function is basically a standalone program, and it says I need these values and I will output what you need. So if I called the function max and I passed it 10 and 20, we'd put them into here and it'd go, okay, A is 10, B is 20. Is A greater than B? The answer is no. Therefore, B is the max. And then it would return B. So this would get a return of 20. So a function is just like a nice way of creating an algorithm that you can just give information and it'll output your answer. Now we do this all the time. Like we define functions in our calculator. The difference is, oh no, it's not really any different because you can define a function in a calculator that accepts multiple variables. So I do this with my students when we do vectors. I allow it to pass multiple variables and it calculates the direction of a vector or the output of a vector. So a function is used in algorithms that's different to functions that we use in mathematics. A block of code that performs a clearly defined task, i.e. outputs the maximum, outputs the highest common factor, and it's separated from the main algorithm, is called a function. You have to define a function before it's used, and once they're defined, you can use it again and again in different algorithms, and all you've got to do is pass it the information that it wants, and it'll output the information that you want. So a function can have one or more inputs, and then it returns an output. So here are two simple examples of functions. If we've got a linear function f of x as 3x plus 2, we can define this function for an algorithm as shown on the right. So we're defining the function define f of x. Basically, if you then say f of 2, if we call this function, it knows that because you've said f of 2, that means that x is 2. So in this program, it then says, okay, we know that they've called it with x as 2, so replace that x with a 2. If x is 2, we get 3 times 2, which is 6, plus 2, which is 8. So now we store 8 into y, and then we return y. So f of 2 will return 8, the value that's in y. So it's just like mathematics. If I created a function called dist, which is for distance, we're going to take out x and y. I'm guessing it's saying the distance between that point, and that's x and that's y. So we're finding this distance here. Because if it was a distance between 2 points, I'll say this one's from a point to the origin. So effectively it's x minus 0 squared plus y minus 0 squared square rooted. So what we do is we pass the we want to find the distance from the origin to some point. So we could say that point could be 2, 4. So if we call distance 2, 4, it then says x is 2, y is 4, 2 squared plus 4 squared. We know that's 20. So distance is the square root of 20, and then it returns the distance. So distance that comes back, this function will return root 20. So functions themselves are super duper useful when you want to reuse code over and over again. Like if you had to keep calculating distances or you had to keep calculating x-intercepts or something. All right, so here, for a natural number n, the factorial function gives n factorial, which is 1 times 2 times 3 times n factorial. Write a factorial function using pseudocode. So what we want to do here is we want to create a function that when we pass it a number, n, like the number that we want to go up to, it'll then return n factorial. Does that make sense? So if I pass it the number 3, it'd find out 1 times 2 times 3. So the first thing we've got to do, if it's a function, we've got to define whatever we want to call the function name. So we're going to call it factorial. And all we need to do is get it to take in a value n. So n is the value that we want to find the factorial of. We've got to have something that holds the number when we multiply it. So we're going to store 1 in the product. You can't store 0 because if you multiply something by 0, it's going to be 0. We want to go from for I from 1 to n. We want our product to be our product times I. End it, our for loop, and then return our product. So let's have a look. We know, just say n was 3. If I called factorial the function with a 3, first thing we would do, we'd get product is equal to 1. Actually, let's put I first, and then put product here. So firstly, our product is 1. That's our initial. From I equals 1, so I is equal to 1, to n. Our product is product times I, so that's also 1. We then go, and I becomes 2. Our product becomes 1 times 2, which is 2. I then becomes 3. Our product becomes 2 times 3, which is 6. We're up to n now, because I is equal to n. They're both equal to 3. So we stop. Is 3 factorial? 3 by 2 by 1, is it 6? The answer is yes, it is. So this thing works. Now, we need to write code that is going to find the evaluation of this thing. So this is a little bit tricky, I guess, because it's something that's new to you. But if you think about it, this can use this function. So we could create a variable that counts from 1 to 10. So to do that, we know it's going to go up to 10, so we could create a for loop. A for loop. So we want to write the factorial function using pseudocode. So we've done that. Using your function from part A, we want to add these together. So let's call it sum. And at the moment, stores 0 in it. We can then say, let's not use I, for A from 1 to 10, sum is equal to sum plus 1 on A of factorial of A. And then end 4. And then we can then print sum. So the first thing, sum is 0. For A is 1, so we say A is 1 to 10. Sum is equal to my current sum, which is 0, plus 1 on factorial of 1. When I put 1 into this, it's just going to return 1. So we just get 0 plus 1 on 1, which is 1. We then go back up to here, and A is now 2. Sum is 1 plus 1 on 2 factorial, which is what this will evaluate. It'll add them together and give us the value of sum, and then it'll do it for 3, and then it'll give us the same thing again. So this thing here, it's going to call factorial, and then factorial is going to return that particular value, and it's going to do it 10 times. And at the end, it's going to output, now I shouldn't put equals, that should be sum is our previous value of sum plus 1 on factorial of A, and that'll pass at that particular value. So that's it. Now you're not going to have to make something like that. The last thing we do, and look, it's really probably definitely not something you're going to do, is called nested loops. So it's when we've got like a for loop inside another loop or a while loop inside another loop. So a nested loop is a loop inside another loop. The first pass of the outer loop starts the inner loop, which executes until it completes. Then the second pass of the outer loop starts, and then it goes to the inner loop again. So the algorithm to the right has a nested loop. Perform a desk check for this algorithm that keeps track of the values A, B, and C for each step. So initially, C is 0. We then, for A is 1 to 2. A is 1. For B is 1 to 3. So we've gone into there, now we're into here. C is C plus 1. So C is the current value of C plus 1, which is 1. We then go back up to the start, so B is now 2. A hasn't changed. And C is now 2 because we had another one to it. We then go back to there. A hasn't changed. B is now 3. C is now 3. Now, because we're up to 3, we then break out of this and we go back to this one. So now A is 2. For B is 1 to 3, so B is 1. C is C plus 1, so C is now 4. We go back up again. A is 2, B is 2, C is 5. We then go back up again. A is 2, C is 3, B is 3, C is 6. So you can see here, these are our values of A, B, and C. So here, once we go 4, and then we come into this for loop. We keep completing this one until we break out of it, and then we go back up and do this one again, and then go into this one. So that's what nested is. It's when there's one inside of another one. Oh, I forgot to put this thing in. So the factorial function can be defined as that on the right, and I forgot to put it in. But we made one up before. So we know factorial takes, we should say define. So define factorial n. We call it product, and it starts with 1 in it. And then we say for I is from 1 to n, product is product times I and 4, and then return the product. Okay, now write another function that will return the value of that. So same here, sum. This one would also take the same value. Define sum of n. Now, because we're summing them, let's say sum and store 0 in that. We would say for I from 1 to n, our sum, I think my pen's gone flat again. It has. Let me give it a sec to recharge. So here, we'd want to get 1 factorial, then add it to 2 factorial, then add it to 3 factorial. Which shouldn't be too hard, because our sum is our previous sum plus factorial of n. So just say I had 1. If I have 1 into that, put it into that, it spits out 1. If I then had 2, if I put that into that, it spit out 2. And each time we're just getting the previous sum and adding them together until we get to n factorial. Okay, right now we'll find the smallest natural number for which n factorial is greater than smallest natural number so we could start with, let's do it in a different color. Store 1 into n, and we could say while factorial n is less than or equal to 10 to the n, n is n plus 1. Print n, and while. So as soon as it stops printing, we know what the value of n is. So to start with 1, it adds 1 to it and then prints it out. So 1 factorial, have I got it as something in here? 1 factorial, and then 10 to the 1. So that's less than that. 2 factorial, let's just put is less than, oh, let's go x factorial. What is it doing? Is less than 10 to the x, given x equals 2. Now, if I said 3, 4, 5, 6, let's go 20. Eventually it'd break, and that'd be the lowest value for n, where factorial n is less than 10 to the n. Okay, now I've grabbed all of the examples from the sample exam so I can go through them. You guys can always try them first. All right, so inputs, the function to integrate, the lower terminal of integration, the upper terminal of integration, the number of trapeziums to use. Define the trapezium. So this is making a function called trapezium. It's saying the function itself is going to take in f of x, which is the function, a, which is our lower value, b, which is our upper value, and n, which is the number of trapeziums to use. So that's all written here. Now, this is the function itself, and it returns the area. Consider the algorithm implemented with the following steps. Trapezium, log ex. So we know at the start, f of x is log ex. We know that a is 1, b is 3, and n is 10. Now, that's our initial setup. Initial. It says the value of the variable sum after one iteration of the while loop. So after going through the while loop once. H is b minus a divided by n. So h x. H is b minus a. It's 1/5. Sum is f of a. Let's say sum is here. Sum is f of a. So if I sub 1 into that, I get 0. And then plus f of b, which is log e3. X is equal to a plus h. So 1 plus 1/5. X is equal to 6 on 5. I is equal to 1. Well, I is less than n. Is 1 less than 10? Yes. Sum is equal to sum plus 2 times f of x. So it's log e3 plus 2 times log e of 6 on 5. X is equal to x plus h. So it's going to be 7 on 5. I is equal to I plus 1. So I is 1, that now becomes 2. Now, the value of the variable sum after one iteration of the while loop. So that's our first iteration. Sum is log E3 plus 2 log E 6 on 5. So log E3 plus 2 log E 6 on 5. 1.4633. So it's C. So that's it. All you needed to know was that that is that, A is that, B is that, N is that. Work all of this out and go through one iteration and find out what the value of sum is. I don't think it's going to be much harder than that. Okay, the next one. Consider the algorithm below uses a bisection method to estimate the solution for an equation in the form f of x equals 0. So once again, we're calling the function bisection. We know f of x is sine x. That value there is a, b is 5, max is 2. What value would be returned when the algorithm is implemented as given? So, if I sub in a and b, sine of 3 times sine of 5, if it's greater than 0, sine of 3 times sine of 5, if f of b, x is in radians. So I've got to make sure in radians. Okay, so radians. So when we multiply them together, we get a negative value. If it's greater than 0, it's not. Return invalid interval. So you can forget about that. I is 0. Mid, while I is less than max. So we know I is 0. I is less than 2. Mid is equal to a plus b on 2, which is 4. If mid equals 0, return mid. Else if f of a times f of mid, f of 3 times f of 4 is less than 0. F of 3 times f of 4 if f of mid is less than 0. What's f of 4? The hell am I doing? So if f of mid equals 0, then return mid. Mid is negative 3. If it's equal to 0, then return we don't. If f of a times f of mid, f of 3 times f of 4, it doesn't know what f is. I didn't define it. Dumbass. Define. Okay. F of 3 times f of 4. That's negative. If f of 3 times f of 4 is less than 0, b is equal to mid. So A is 3, B is 4. I is equal to I plus 1. Okay, if I is less than max, it is. Mid is A plus B on 2. So mid is 7 on 2. If f of mid equals 0, then return mid. So f of 7 on 2, it's negative. F of mid, if f of A times f of mid is negative. F of 3 times f of mid, that is negative. Then B, put mid into B. So B is equal to 7 on 2. The value, okay, then I is equal to 2. And then we know 2 is not less than max. And while return mid. So we know mid is 7 on 2. So our answer would be D. So here, stupid bloody thing. I just got to let it charge for a sec. It's supposed to recharge up to 30% in like 3 seconds, but it doesn't. Okay, we should have enough now, I'm tipping. Okay, so I is equal to 2 because I'm adding 1 to it. And then when we go up here, is 2 less than 2 because max is 2? The answer is no. So we return mid, and we know that mid is now 7 on 2. Because I said mid was 7 plus 3 on 2. I don't think I wrote it down, but I should have. So it's 3 on 5. Okay, one way of implementing use method using pseudocode with a tolerance level of 0.001 is shown below. The pseudocode is incomplete, with 2 missing lines indicated by an empty box. So there's your function. X0 is your initial estimate. Jesus, this is actually pretty complex. Like it looks like it. Newton f of x, x0. So that is your function, and then that is your initial value. The derivative of f of x is stored into dfx. 0 is stored into I. Previous value of x is your initial guess. While I is less than 1,000, next x is your previous x minus f of your previous x over your derivative of f of x. So if the tolerance level is 0.001, your next x minus your previous x if the difference between them is less than 0.01, we want to return our next x. So if your new value take away your old value has a difference of 0.001, we want to return our newest value. Oh, hang on, but we want a tolerance level of 0.001, so it can be above or below. Okay, so between, I think it's going to be E, because we want to go between, we can go 0.001 below or 0.001 above. it's the top value minus it's the new value minus the previous value, and we always want to return the newest value because that one's going to be the closest. And that's exactly what it is, E. So because the tolerance level is 0.001, it means it can be to the right by 1, so it's got a difference of 0.001, or it can be the left by 0.001. It can go either way because it's within that tolerance. And you've got to return your latest value as the guess. So that would be your second last value. That would be your second last value. So you can scrap them. And you always want to do your newest value minus your lowest, your previous value, not your previous value minus your newest value to find the difference. But I think that's pretty hard. I don't think many people are going to get that straight away. Okay, and this is the special one. Now the special stuff seems to be easier. Declare integer n, f, t1, t2. Set f to 0, t1 to 2, t2 to 3, n to 3. Repeat 3 times. Okay. So repeat 3 times. F is equal to t1 plus 2 times t2, which is 8. t2 is 8. Print f. So that's going to be 8. Go back up to the top. So that was once. The second time, f is equal to t1 plus 2 times 8, which is 16. So that's 18. t2 is 18. Print 18. The third time, f is equal to t1, 2, plus 2 times t2, which is 36. So that gives us 38. t2 is 38. Print f, which is 38. So the final number in the list, because we wanted to do it 3 times, is 38. And there's our answer, 2C, 38. Okay, so hopefully this has shed some light. Like I said, nested loops, not likely. Basic understanding of functions, like being able to see that when you call a function, like trapezium, that value corresponds to that value corresponds to that value, that corresponds to that value, that corresponds to that. And then when you return a value, that's the value that's going to get returned by the function. But in here, it's asking you for the variable sum. So it's asking you what the value of that is after you've gone through that once. Now this is way longer a video than I wanted it to be, but hopefully you've got an idea of the basics of this now, because it's not very clear in the study design. All right, best of luck. Bye.